Okay, out of curiosity, I've noticed we got operating systems, algorithms, and AI back to back in this room. Any of you in all three of them?
Oh, that would be rough.
So somebody is?
I'm in two.
Yeah. Anyway, no good reason to ask, but before we get started, any questions or problems about anything? Yeah?
When would you like us to do those readings? So I saw on the modules it's after class, but do you want us to do it before the week, or when do you want us to do those readings?
So yeah, in the modules I put the reading associated with the lecture
Okay.
when I remember to. So I'll do it before the lecture if I can.
Okay.
Any other questions? All right, so later today, the first problem set will come out, and it'll be due the end of next week. I'll also be posting consulting hours, TA hours for next, which will start next week. Okay. All right, so in 2420, I know you did a lot of timing algorithms, and we just do a little bit of that in 4150. Just this next assignment will be one of the problems will involve doing some experiments. And so I just wanted to talk for a while today about what I see as the right way to do timing experiments. So let's discuss for a minute what would be wrong with just, let's say you wanted to know how long a piece of code takes to work, or it takes to run. Taking that code, starting a timer, running the code, stopping the timer. That's how long it takes to run. Okay? What's something wrong with it? Yeah.
Well,
I'll get you.
it might get scheduled out. So.
Okay, you said it might get scheduled out. The operating system might not run it right away, might interrupt it while it's running. Yeah?
It might add in the spin up time, the time it takes for the algorithm to actually start and running.
Okay, so in a lot of programs these days, a lot of programming languages, the first while that a program runs, it's slower because the code is actually being compiled before it runs, and various other things are happening. Yeah?
Oftentimes these programs will run in fractions of a second.
Say it a little louder.
They'll be running in fractions of a second.
Okay, they'll be running in fractions of a second, so your timer had better be pretty good resolution in that case. Yep.
You might run into weirdnesses with it looking slower because a bunch of cache misses the first time you run it.
Okay, so that's another aspect of sort of warming up the program. May take a while for memory to get loaded from into main memory and then into cache. Yeah.
If it's ever preempted, you'll probably have to deal with reliving the TLBs and everything, and having reload all the memory, and I might end up with random slowdowns in the middle.
Okay, so more random slowdowns that could happen. Yeah.
That's only one sample. We should time it more than once.
Okay. He says that's only one sample. Perhaps we should time things more than once to get an average. Yeah.
The time to create a process is typically really long, especially on Windows NT.
Okay. So lots of good answers. So let's just go through my timing guidelines. And first thing, a lot of these had to do with making, or some of it had to do with making your computer quiet. I mean, ideally, the only thing going on in your computer would be the code you're timing, but that's kind of difficult to arrange. But at least look at the performance profile on your operating system and make sure that there's not some runaway process that's hogging all the time right now, and shut down anything that you don't need to have running. Get your computer to be as quiet as possible. That's sort of an easy thing to do. Warm up, that's not really a technical term, but warm up your code before taking data. Run your program for a while before you start paying attention to the results. And I'll show you a way I like to do that shortly here. That lets lots of things happen. Libraries load, the just-in-time compiler runs, the cache populates, and so on. Okay, never time small intervals. And of all the guidelines that I have, this is the one that's always proved to be most controversial with people coming out of 2420. I once had a sort of a big argument with a TA in 2420 about this point. And by that I mean, you can get these timers that time to the nanosecond, but they're not really that accurate. They give you the answer in nanoseconds, but that doesn't mean that necessarily you can trust that. And rather, let's say, I think you all know that you need to, if you're timing a thing that doesn't take much time, you want to time it a bunch of times and compute an average. But I'm going a little bit further. I'm saying you time it a bunch of times, not by starting the clock, doing the thing, stopping the clock, noting the time, doing that again, start, stop, start, stop, start, stop, get a whole bunch of times and average them. The analogy I like to give is if you've ever had your pulse taken by a nurse without, with finger on the wrist, does the nurse do this? 1, 2, 3. What does a nurse do? Times it for like 15 seconds and then averages over the 15 seconds. Makes one measurement and then computes an average. Doesn't make, the analogy here would be you don't make 1,000,000 measurements and average those 1,000,000 measurements. Make one measurement and divide it by 1,000,000. Okay, so don't time small intervals. In my timing code, I try not to time anything that takes less than a second. That's probably overkill, but a second's not very long for me, so no big deal. Okay, and I'll show you how to do that. Now, when you do that, you got a problem, because you're not just timing the thing that you care about, you're timing the loop that's running the thing you care about. And often, the overhead for that loop that you're timing, in addition to what you care about, is negligible. Sometimes it isn't. And so another thing you can do is compute the average time it takes, for the loop to run, and then run the same loop without the thing in the middle you're trying to time, and subtract the difference. So you can figure out how much the overhead is. Now, also in my code, I like to just print out, for sanity's sake, the difference between the thing I'm timing and the overhead of the loop, and make sure it's a couple of order of magnitudes different. If that's the case, the timing loop isn't going to affect things. In any event, you can subtract off the overhead, and sometimes you need to revise your experiment if the overhead is significant. You want to make the overhead as little as possible. And finally, you need to carefully design your experiment. You've got to know what you're trying to measure. So what if you're trying to measure the average case of selection sort? How do you determine you've got to figure out an array to sort. So how do you do that? How do you figure out the average case of a sorting algorithm? What do you time?
How long it takes to sort of randomly distribute it.
He said you could time how long it takes to sort. You take take an array of length 100, randomize it, shuffle it up randomly, and time how long it takes to sort it. Okay, is that good? Can we now say that's the average time it takes to sort an array in selection sort? How could you improve on that? Yep. Yeah, do it a bunch of times. Time how long it takes to sort a whole bunch of different randomly generated arrays, and then compute the average. Now, what if you want to figure out the worst case running time for selection sort?
I don't remember what the worst case for selection is.
Well, yeah. So I hear there's some speculation about it. You have to know something about the algorithm in that case. You have to figure out what the worst case is. So a lot of times, like insertion sort, the worst case would be it's sorted in reverse order. And so you would time that. Or for the best case, it's for insertion sort anyway, it's if it's already sorted. So there you kind of know what the best case and the worst cases are, and you test them. Now, the second point is very important. Now, I always get people that ignore this advice on their first assignment. And that is, we're interested in determining the rate of growth of the time the algorithm runs as the input size grows. And to do that, clearly, you've got to time how long it takes to do different sizes of inputs, in the case of sorting different lengths of arrays. Double the size each time. Start small, and then double each time until you get big. Maybe go from like 1,000 to 1,000,000. That would be 10 doublings. Or 100 to 1,000,000, something like that. Double each time. And we'll talk about why that is, but the bottom line is, if you can look at the a doubling behavior, what happened, you can basically, by looking at the doubling behavior, you can say what the order of growth is. You don't have to do any fitting equations to curves or anything. You can just tell from the table. So we'll say more about that today too. And I guess we'll say it right now. Okay, doubling behavior. That's what I call the relationship between f of n and f of 2n for different f's. So these are some f's that we commonly see when we look at algorithms. The first one is constant. So a constant function never changes, a straight line if you graph it. The next one is a logarithmic curve. Okay? Now you'll notice that I don't give the base. I don't say whether that's log base 2 or log base 10 or what. How can I get away without saying what the base of a logarithm is? Yeah?
Because the conversion between log bases is a constant.
Okay. So we said the conversion between two different bases is a constant. Essentially, you can compute you can convert log 2 of something to log 10 of something by multiplying by the correct constant. So we've already got a constant sitting here. So if you use a different base, it just changes the constant, but it's still a constant. So we don't really have to worry about the base of the logarithm most of the time. Okay, we've got linear functions, which would be a straight line if it's graphed. We have n log n, which I don't have a name for it. We just call it n log n. Then we got a quadratic curve, a cubic curve, and an exponential with the basis 2 in this case. So what I want to do is figure out how to, let's say you have an algorithm and you time it for n equals 10, and then n equals 20, and then n equals 40, and then n equals 80. How can you look at those timing results and just tell from the results what kind of thing you're looking for? So the first one's pretty easy. How do you know after you've done a series of times, you've timed for sizes as they double, how can you tell if you're dealing with a constant function? It won't change. Okay? So if it takes 100 milliseconds and then 101 milliseconds, then 99 milliseconds, then 100 milliseconds, it's never going to be perfect. If that trend continues, you're dealing with a constant function. And that's easy to see. So, and just to make a note, if you take f of 2n and subtract f of n, you expect to see 0, because in both cases the answer is going to be C. So the doubling behavior is it stays the same. Now, what about a logarithmic curve? What if you're dealing with something like binary search, logarithmic running time? What would you expect the doubling behavior to be? What would you see in the table as the sizes double? Yep.
If the size is double, then it only goes up by one comparison or one measurement.
Okay, so if it's logarithmic, it only goes up by one comparison or one. I don't remember what else you said, but I mean that's true if you're counting comparisons. But what if you're measuring time? Yeah.
The time would go up, but not quite double.
Well, he said a time would go up, but not quite double. We can be more specific than that, actually. It doesn't double. That's true. Yeah.
Well, it would be less than linear. It would be like curving.
Yep. It wouldn't go up as fast as a linear function. Yeah.
This goes up by a constant.
It goes up by a constant. Okay. So let's see how we can see that. So if we took f of 2n and if we did that subtraction again, we did subtraction, we would get, we're doing c log of 2n minus c log of n. And what I've replaced is c log of 2n, I replaced with this expression right here. C log 2 plus c log n. Where'd that come from? It's just the rule of taking the log of a product. Log of a product, so log of 2n is log of 2 plus log of n. That's a handy thing to remember. Then you subtract out the log n's and you got c log 2. That's just a constant. So it doesn't depend on n at all. So the difference is a constant. So if you see a timing like it goes from 10 to 15 to 20 to 26 to 30 to 34, whatever, that's looking like a logarithmic curve. Okay? So I'm trying to justify why we're interested in doubling behavior, because we can just, we don't have to work too hard to figure out what kind of curve we're looking at. What about a linear function? It doubles. Doubling the size of n doubles the size of the function. Right? And to see that here, instead of subtracting, I'm going to divide, because we're not talking about differences now, we're talking about ratios. So I get f of 2n divided by f of n is the same as 2cn divided by cn, and the answer is 2. So when you time out a linear algorithm, linear runtime algorithm, you'll, once n gets big enough, it'll settle down to doubling. The runtime will double each time, roughly. And you can tell. Now, no one's asked this yet, but I always get it, so I'll ask it myself. Why did I subtract for those first two? I subtracted f of 2n minus n, and I divided for the third one. Yeah?
You could still subtract for the third one, it just is a little bit more confusing to understand what that actually does.
Yeah, so we said I could subtract for the second one, and actually we're going to subtract all the way, we're going to divide all the way down. It's just that it turns out that for linear and quadratic, it's useful to look at ratios. It's the ratio that tells you the difference. And for the simpler ones, first two, it's the difference that tells us what's going on. I mean, we could have divided with the first one, and then what would the rule be? Yeah, if you double, the ratio is 1. Or instead, I said the difference is 0. It's the same thing. It's just, I think it's easier to see just to say the difference is 0. And if we divide it in the second case, I don't think we get a particularly nice result. I mean, I guess you could come to learn that, you could learn to recognize it looks like a logarithmic curve, but just, you want to look at the difference in that case, because it's really simple, it's a constant. Just whatever reveals the behavior the best. So if you've got, what if I give you a table of numbers, of measurements, and ask you to figure it out? Right? You've got to sort of look, you've got to eyeball and say, I think this is logarithmic, let's test it. And then you would subtract successive values to see if that's a constant. And if it's not, you say, oh, maybe I should divide and see if it's linear. Okay, here is, I've already revealed the answer, but what happens when we're dealing with n log n? What's the doubling behavior of n log n? You can read it right there. I have the ratio of f of n over f of 2n over f of n.
Constant over log of n plus 2.
Well, let's see. There's this plus 2 here. So it's 2 plus some other stuff. Okay? So it at least doubles, right? The ratio was more than 2. What's this other stuff going to be? 2 log 2 is a constant. Log n's not. But what can you say about that? The cruft in front of the plus 2. Yeah?
The trend to 0 and increases.
Right. As n increases, that goes towards 0. So as n becomes large, it tends toward doubling each time. So it's hard to tell an n log n, tell the difference between an n log n growth and an n growth, linear growth. And in fact, an n log n algorithm just isn't that much worse than a linear algorithm. So I just say it doubles plus a little more. But I might as well have said, I could have said for the second one up there, instead of increases by a constant, I could have said stays the same plus a little more. That wouldn't be quite as precise. But that's about the best I can do for n log n. What about quadratic? N squared. If you double the size of the input, what happens to the? It quadruples. That's easy to see. It just goes 2n squared is 4n squared, and divide out, you get the 4. What about a cubic algorithm? Octuples, whatever, goes up by a factor of 8. Yeah. And then exponential. Well, there you have 2 to the nth. What happens when you double n? Yeah, let's see. So I've got 2 to the 2n. I square that. I get f of n squared, right? All right. I didn't square this, I just refactored it. So 2 to the 2n is the same as 2 to the n squared. 2 to the n right here is the same as f of n. So this is f of n squared. So double the size of the input squares the size of the output. And that doesn't even take the leading, I didn't even put the leading constant here in because it kind of messes things up, makes it harder to see. But the truth about exponential is it grows so fast that this is one exception to my assertion that you should double the size of the input each time. Because it will quickly become so large that it will take too long to run the program. The time will be too long. So instead, if you suspect something's exponential, what you should do is just increase the size of the input by 1 each time. And see what happens. And what do you expect to see if it's a 2 to the n exponential and you increase the size by 1? Doubles. So you go from 10 to 11 to 12 to 13, it doubles each time. And that's easy to see there because 2 to the n plus 1 divided by 2 to the n is just 2. Now there are lots of other kinds of exponentials. 4 to the n, 6 to the n. In general, if it's 6 to the n, it'll go up by a factor of 6. Okay, so that's why I like doubling behavior. You just do some timing measurements as things double and see what happens. Now, when I ask you to do a timing measurement, be sure of a couple things. Your table ought to have the sizes, ought to see them doubling, assuming that we're talking about, well, it depends what we're talking. Well, yeah, I should see it doubling, unless it's exponential. I should see the time it takes to run. And most people get that right. What's the other thing you ought to put in a table, given what I just said? If you're going to argue that something is linear or logarithmic or quadratic.
The rate at which it increases.
Well, specifically, what should we put in the third column? Yeah. Well, what do you mean by doubling behavior?
Like every time it doubles, how much does it increase on average?
Okay, so what I want to see is either, depending, I'll take one more answer, yeah. No, not the big O. We're doing this to determine the big O. Yeah?
Is the ratio between that measurement and the previous
Right,
one?
the ratio between each measurement and the previous one, or the difference, depending on what kind of thing we're dealing with. Because that's what really seals the deal about what the complexity is looking at the ratios or the differences. So you don't want to leave that out of a table that you're doing to do this sort of analysis with. Okay, now you'll notice I've hardly said anything about big O notation. This is just sort of another way to approach the same idea. If we're interested in what happens to the running time of something, of some algorithm, as the input size increases. And one way to characterize it is with the doubling behavior. An equivalent way is with big O. We'll do that, but not right now. All right, now I'm going to show you some code that actually does some timing, show you how I achieve all my goals. This code is written in C#. So what I do up here is I have some constants I've defined that don't really matter that much. Here's the main method. First, I print out some information about the stopwatch class, whether it's high resolution and how frequently it ticks, just so we can see. And then you can choose one of 10 choices, one of 10 timing experiments to run. And it tells you how long it takes. So let's try running it. That's unfortunate. Hold on. Okay, let's take choice 1. So it's timing something in there. So it's figuring out how long, given an array, a sorted array, it's trying to figure out the time it takes to do a binary search to locate what we know is the last element in the array. So what it does, it creates an array, sorts it, figures out what the last element is, and then calls a binary search algorithm to look for it. And apparently that takes 0.13 milliseconds. What do you think right off the bat? Let's say the array has 1,000 elements. I'm just guessing.
Well, that's what I think right off the bat is what is n, because that affects our time.
Yeah, it'll certainly affect the time. Let's say it's, well, I don't have to guess. Let's go look. So if we go down here to approach 1,
We get a macro for the size.
okay, I had to go back where I was. Shoot. Its size, yep. 1023. 1,023 elements, and it took 0.13 seconds to do a binary search.
What happens if it's double?
Well, I just want to know that one measurement. You think that's an accurate? Would you expect a single binary search on a 1,023 element array to be faster or shorter, or does that sound about right?
I feel like it should be faster.
It sounds really slow.
It feels
Yeah,
slow.
a tenth of a second is really slow. Especially, how many probes will a binary search have to do to find this element?
Like a full 10.
Like 10, log base 2 of 1023, which is 10. So let's see how it did it. It constructed a sorted array. It just put the numbers 1 through, 0 through 1023. It created a stopwatch. It then started the stopwatch, made a one call to binary search, stopped, and then reported the number of milliseconds in that interval. Okay? So if that's the way you do your timing experiments, you get really sloppy results. Yeah, that's how long that call took, but that's not a very good way to evaluate the algorithm. How did we screw up? How did I screw up?
Did you give it time to warm up?
Yeah, I didn't give it time to warm up. It was a cold start. I just said, okay, time binary search. And it took a while to get going. There's not much going on in the algorithm itself, but to get the method off the ground and get it running took a long time. So that's an embarrassing result. Let's try a different one. Let's do choice 2 and see. So now it's timing 1,000 searches and averaging them. And we got something quite a bit smaller. You trust that one?
Yeah, for the most part.
And given that there are 10 different examples to show you, maybe not, but okay, 0.005 seconds.
Certainly better.
Yeah, that sounds like more like the truth. Let's go look at how that's done. Again, I construct a sorted array just like before, but now what I do is I write a loop that runs for, I think that's 1,000. I start the watch, I do the search, I stop the watch. Okay? I do that 1,000 times.
1,000 taps.
So now instead of timing 1, I'm timing 1,000 and averaging them. Okay? And we've got a different number, but should we trust that one?
No.
Okay? So what's wrong now? Yep.
Still doing a cold start because you're
Yeah. We're still doing a cold start. Those early calls to binary search are going to take longer than the later ones. And there's another thing that we violated that I talked about. Yeah?
Maybe overhead?
Well, not overhead. In this case, I'm not worried about overhead. What am I worried about? Yeah?
You're doing 1,000 little measurements instead of just the one.
Right. I want to just do one long measurement instead of a bunch of short ones. So I'd like to time the whole loop and then divide by 1,000 as opposed to the net effect of starting, stopping is that the clock advances a little bit each time, and we figure out how much the call down here in the milliseconds of stopwatch just tells us the total elapsed time. But I'm going to do one timing measurement because that just strikes me as being a better idea. So let's look at the next one here. Time binary search 3. We construct a sorted array, create a stopwatch. Now I start the watch. Then I run the loop. And then I stop. And then I display the average. All right? So let's try that out and see. So it was 0.0005 before, I think. Now it's half that. Yeah?
You had the overhead running before them.
Okay, so a couple things we have. There's the overhead of the for loop, but even with that overhead, notice we got a smaller answer. What else is bad about the way I'm doing it now? Yeah?
The cache isn't very long. Maybe you should run it like
Yeah, we're not warming anything up. There's no warm-up happening here. We're still running afoul of that. So let's look at my next one. Okay, here I'm I'm timing the loop and calculating the average. And then down here, I'm doing the same thing, but I'm timing a loop where I've commented out the actual call to binary search. And then I can, later on, I can subtract the overhead average from the total average. So that's my first attempt to try to deal with the overhead question. So let's run that and see. What was this, number 4? So you'll see I printed it out, so it took 0.00028 milliseconds for the whole thing. The loop by itself was 2.8 times 10 to the negative 6th, so it's a couple of 1 or 2 orders of magnitude smaller. When you do the subtraction, you get the same answer in 2 digits. So that shows us that, yeah, we've accounted for the overhead and it wasn't much. And we're still getting the same answer. So that's good. The overhead isn't causing any problem. What do you think, what problems do you see with this one now? There's still the warm-up problem. And another thing that's more subtle is that's probably going to be a very fast thing right there. It's harder to time this it's harder to time this thing in yellow accurately than it is to time this thing accurately, just because this thing now takes longer. So we need to take that into account. Let's see what the next one looks like. All right, now here it gets a little more involved. So I have this variable elapse, which starts out at 0, and repetition starts at 1. Then I enter this loop. So what I do is each time I enter the loop, I double the number of repetitions I'm going to do by 2. I restart the watch, so I start it from 0. I do the timing that I care about, that long-running loop. I stop the watch, and I figure how much time has elapsed. And if less than a second has elapsed, I do it all again with twice as many repetitions. So the first time through the loop, first time through this outer do loop, I time this thing here, or actually I time this thing here twice. And if that didn't take a second, I say how long it takes to do 4 of them, and then how long it takes to do 8, and then 16, and then 32, and then 64, until finally I find a value for repetitions that takes over a second to do the one timing that I care about. And then I use it. And so what I then do is I take the elapsed time for that last time through the loop and divide it by the repetitions the last time through the loop, and I get an average. Now what does that accomplish?
Solves your warm-up problem.
It solves the warm-up problem. Okay? So if the last repetition took a second, the next to last time through the do loop, how long did that take? Half a second. And the one before that was a quarter of a second. The one before that was an eighth. And the one before that was a 16th. So what is, and all those previous ones we were ignoring the data for. So what is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32? It's 1. So you're warming the thing up for a second and then timing for a second. That's what this accomplishes. Okay, and the only thing that can go wrong is if the thing you're timing takes more than a second in the first place, then you're kind of blowing the warm up. So you got to make sure that's not the case. Usually it's not going to take that long. All right. What about the overhead, though? The overhead of the loop. We can compute it the same way. We compute the average time, the average overhead for a single run through this loop right here. And then we subtract and display. Yeah?
Is there a reason you made a new stopwatch for the overhead instead of restarting the other one?
No, I don't know why I did that. Probably just copy and pasted.
Okay.
Yeah?
This might be stupid, but why are we computing the overhead if we're interested in like differences in ratios? Why I would assume that the for loop would be like pretty constant between the initial one and the one that we're doubling.
Yeah, I mean, it's just I'm just trying to do a complete job. So up here, I really just want to time this. But I'm not allowing myself to time something that takes less than a second. So I've got to time the loop. And then, to be perfect, I've got to figure out, okay, how much did the loop contribute to this as opposed to the call to binary search? Then I can subtract out the difference. Now, if I actually run this, you'll notice, again, that the loop overhead is negligible anyway. So this is number 5. And this is taking longer now. It's going to take about 2 seconds. And I think our answer last time was like 0.00028 or something like that. So again, we're about half as big now. Now, test 1 was obviously flawed and wrong. But test 2, 3, 4, 5, yeah, you could have believed those answers were right. And it's tempting to believe the first number you see. And maybe you're wondering whether this number is right as well.
I'm assuming it's not because we have 5.
Well, I have more variations on the theme, but I think this is about the best number I can contrive to get. Yeah.
In your kind of guidelines, you say to have kind of realistic numbers that are more random, and here in these tests, you still have just 1 through.
Okay, in fact that's what some of the other examples do.
Okay.
So what he's pointing out is that this test is showing the average time it takes to find the last element in an array using binary search. And if we want to know the average time in general, we can do a different experiment. Yeah?
Does C# do any optimizations when it compiles that?
Okay.
Might mess this up.
Right, so he's asking, what about optimizations? Because if C# took this and said, oh, look, they're never even doing anything with the result, let's just optimize the entire thing away, then we would get really inaccurate results. And I don't believe it's doing optimizations in this case. I don't know if it's smart enough, if it's just not doing any because we're not doing it in release mode, or if it's smart enough to see that we're actually timing things and knowing that stuff does matter. But it is something you take into account. If you time something and it keeps taking 0 seconds, that's a good sign that something's being optimized out. Well, let's look quickly at the other cases. So that's that. The key thing, the heart of this is this idea. This idea right here of sort of, with one tool, we are taking care of the warm-up, basically warming up for a second and then timing for the second. And we don't know in advance how many repetitions to use, so we just keep trying until we find the right number. And the effort isn't wasted because it does the warming up. So when you do your timing experiment, do something like that. Not hard. Okay. Okay, this returns the average time required to find an element in an array of a given size using binary search, assuming that the element we're looking for appears in the array. So we need to do something different than always looking for the last element. How can we do this? I can think of 2 reasonable ways to come up with an average. Okay, so one thing we could do is, create an array 0 to 1023, pick a random number from that interval, and look for it, and then do it again with, each time picking a random number. That'd be one way to do it. Pick a bunch of random numbers, average the time. What'd be another way?
Randomize the array and then search for the same number every time.
Well, randomizing the array, we could do binary search then.
Oh,
It needs to be sorted. Yeah? Yeah. If it's only 10, 20, 10, 24, or 10, 23 elements, yeah, just look for them all. And time that. If it's like a billion element array, maybe you don't want to do that. You want to do more of a sampling approach with random numbers. But for an array this small, we can afford just to look up every one once. And so you'll see that what I do here is it's now a little more complicated because what's inside here is different. So before, what was inside that outer loop, which isn't highlighted, was just a call to binary search. Now it's a call to that calls binary search once for each number in the array. And then we do the averaging looks different too because there are more things to average over. But same idea. So let's see how long that takes. So before we were measuring what was it, 0.00016? Okay, so it comes at 0.00018. So for whatever reason. Okay. Let's look at number 7. Okay, this runs using a different timer. So the stopwatch uses what you call wall clock time, basically elapsed time, independent of the computer. This one uses a timer, a process timer. And the way it's supposed to work is it times the amount of time the process runs. So if it gets swapped out and doesn't run for a while, the timer doesn't increment while the code isn't actually running. So in theory, it should be more accurate. This is the same thing we just did, but with using the process timer. And we got the same thing. No, yeah. Actually, in this case, the overhead round-off error made it be slightly smaller. So, okay. Let's see what's next. Okay, this is linear search. Average time to find an element in an array of the given size using, this says binary search, but actually this is linear search. So that would be number 8. So what you notice, I'm displaying the size and then the time it took and then the delta. And in fact, it says binary search. I said it looked like it was calling a linear search method, but what's going on here? Are we doing a binary search or a linear search? What's the numbers tell us here? Yeah, the difference each time is roughly a constant. You know, it's not perfect, but it's, you know, pretty close. Plus, I labeled the column delta, so it must be it's a difference. It's not a ratio. So the difference here is I'm just running I'm running through a bunch of sizes and computing averages that way. Okay. Let's try number 9, which I think really is linear search. I think I just scrolled too far. No. Okay. We'll do number 10. That must be the linear search one. There we go. So now I'm displaying ratios. And what do you expect to see now?
That it doubles.
You should see it double each time. Now for small arrays, 1.92 is pretty close. And it's not perfect, and you often see anomalies often when the array gets so big it doesn't fit in the cache, for example. You'll see fluctuations. It gets really huge and doesn't fit in the main memory, which is kind of impossible these days. You'll see wackiness too. But as you go along, it'll converge toward 2. Now, like I say, it's not going to be absolutely perfect.
Oh, that's the ratio.
Yeah, this is ratio.
I thought that was the difference.
Yeah.
I can't read.
I bet the next one will be closer to 2. Okay? And if you saw what was coming out were roughly 4s, then you'd have quadratic. Okay, any questions about this? This actually won't be a major aspect of the class. You won't be doing nearly the kind of reports you did in 2420 on algorithms, experimental analyses. Yeah?
Is the ratio test the better interval from doing like a check analysis with like dividing T of n by F of n?
Yeah, it's both give you the same result. I just like this because you can just eyeball it. You don't have to do anything. You just look at the answer, come out and see what it is. Okay, let's take a break and then we'll look at something else. All right, I'm going to ask you a couple questions. What does it mean if I say this? If I say f of n is O of n squared, what am I saying? Okay?
The worst case timing scenario of that function is n squared.
So we said the worst case timing scenario of that function is n squared. So I'm going to take issue with one thing you said, which is worst case. Okay? Big O doesn't mean worst case. I would use a different word to describe big O. Yeah?
Are we saying average case instead?
No. You can use big O to describe worst case. You can use big O to describe the average case. You can even use big O to describe the best case. But that's not the best word to use to describe what big O means. Yeah? Say again? Still didn't get it. Well, it's a way of doing time complexity, of characterizing time complexity. Yeah?
Is it the complexity as n approaches infinity?
Well, it has to do with n becoming large, but yeah?
The upper bound.
Upper bound. Okay, big O is for giving the upper bound on what? What's it give the upper bound of? Yeah?
The way a function grows.
Yes, rate of growth. So big O n squared means that the rate of growth of f of n, in other words, its doubling behavior, is less than or equal to the rate of growth of n squared as n goes in the limit, as n goes to infinity. Okay, so it's an upper bound on the rate of growth. It's often used, it's most often used to describe worst cases, because you usually want to give upper bounds on worst cases and lower bounds on best cases. But you shouldn't think of it as meaning upper bound. We can put an upper bound on the best case. So it's an upper bound on the rate of growth as n goes to infinity. Okay? So we'll talk more about this. I just want to get that out there right away. Now, let me ask you another thing. What does it mean when I say selection sort is O of n squared? Yep.
As the length of the array that you're doing selection sort on increases, the upper bound of the time increases by n squared.
Okay, so yeah. So essentially, we're saying the same thing that it says right up above there. It says the upper bound on the rate of growth of selection sort as the length of the array gets larger is n squared. In other words, the doubling behavior is it quadruples when you double the size of the array. Okay, but there's one fine point I want to make here. What if I said instead of selection sort is O of n squared, what if I said it was O of k squared? Or if I said it was O of m squared? What, does it matter? Yeah.
Depends on what you define n, k, and m to be.
Right. He said it depends on what you define n, k, and m to be. So up here, it was obvious what n was the a variable that shows up in f, and so we related f of n to O of n squared. Down here, this isn't quite right because we're not saying what n or k or m is. So if I want to say selection sort's O of m squared, I would add where m, that's not very good, m is the length of the array. Now, you always need to be specific about what that, if you're saying something is O of n squared, you need to say what n is. A lot of times you sort of assume, if you're talking about sorting, you assume it's the length of the array. Sometimes it's not obvious, so you always need to be specific. And furthermore, we're going to do lots of this in this class, comparing different algorithms to each other. And in order to make sure we're doing an apples-to-apples comparison, if we're doing O of n squared or O of n log n needs to be a measure of the size of the input to the algorithm. We always want to make sure that when we talk about time complexity, we talk about it in terms of the size of the input. So if we're talking about the length of the array being sorted, is that a measure of the size of the input to the sorting algorithm? Yeah. The input gets larger, n gets larger in a linear fashion. Sometimes it'll be a little, I won't go into it right now, but sometimes it's a little harder to decide what the right way to characterize the size of the input is. For sorting, it's clear. Okay? Is big O always used to put bounds on running time?
No.
What else could it be used for?
Memory?
Yeah. A common thing is memory. Sometimes we want to talk about how much memory does the algorithm use. And again, we put a big O bound on it. So it's often used to put upper bounds on running times, but it can be used to put upper bounds on memory consumption or anything else you could measure. Yeah?
So that's why when we define big O, we just use it as rate of growth and we don't mention time?
Right. Yeah. Yeah, so he said, when I said, my definition was upper bound on rate of growth, right? rate of growth of, well, in this case, rate of growth is clear. We're talking about the value of f. But over here, when we're talking about selection sort, the rate of growth of running time or rate of growth of memory consumption is, we need to be more specific. But by default, we're talking about running time. Yeah?
So what if we have two variables that are relevant, like 2 days ago when we were talking about the, was it Boggle or whatever? Where it's not just about how many words are in the dictionary, but also how long the average of those words are.
Okay. So talking about the anagram problem last time. So we saw that the first algorithm, jumble 0, if you held k constant, the length of the word, the running time was n squared, right? And if you held n constant and let k vary, it was k factorial.
Yeah.
So you do this. You just say the upper bound on the running time, the running time is bounded above by n squared k factorial, where n is the number of words and k is the number of letters in each word. So we tend to see expressions like that, not exactly like that, but complexity expressions with more than one variable when we talk about graphs. But for sorting, we only see the one. Any other questions? Okay, so let's look at what I have to say about big O notation and its brethren. Okay, here is selection sort. Well, that's one way to think about it. That's the code for selection sort. But actually, maybe it's been a while since you looked at selection sort, so let's look at it this way. All right, so this is what I call a scatter plot. The idea is that this is supposed to represent an array, where think about this horizontal axis as being the indexes into the array. So this array contains, this looks like 16 elements. So the indexes run, this is index 0, index 1, index 2, index 3, index 4, and so on. The vertical axis is the value of the thing. And so this box right here, its value is 0. This box up here, its value is 15. And so that's what a sorted array looks like. Element 0 of the array contains the number 0. Then element 1 contains the number 1, and so on. On the other hand, if I permute it, then it's all scrambled up. Now, where is the smallest element in the array? Right here. And whatever index that is, that holds the smallest element. And up here is the largest element. And when we sort it, of course, it'll be a straight line. If we sort it in descending order, what would it look like?
Straight line the other way.
Straight line going the other way. So I'm trying to build up your intuition about how to look at this picture and make sense of it. Now, what I've done is I've instrumented the sorting algorithms that I've implemented some sorting algorithms, and I've written them so that every time the algorithm compares two numbers, it colors the boxes being compared red. And then when it swaps them, you see them swap. So it animates the algorithm. It's tied directly to the algorithm. So swaps, you actually see them swap. Otherwise, you see flashing red. So if we permute this thing, and our algorithm is selection sort, and we set the speed to slow and start, let's see what happens. All right, you can see it start to rearrange itself. Now those vertical lines right there are an artifact of my display. I need to fix it here. For some reason, if I 125%, it has some round off error in it. Okay, so let me make it a little bit bigger. I can't see all the numbers here. Oops. Try this again. Okay, we'll put the speed on slow, and I'll start selection sort. So who could remind us how selection sort works? Yeah.
Does it get the
All right, so it makes a pass through the array, it finds the smallest one, and swaps it into the first location. Then it makes a pass through the rest of, all except the first element, finds the smallest remaining one and swaps it in. So I'll do it again, and you can see, you'll see that happen. Watch, so this guy here is in the first pass, it's going to eventually get swapped over to here. Okay, got. So there are two nested loops. There's the loop that's sort of looping through the passes. Each pass has a loop that looks through the rest of the array to find the smallest remaining element and puts it in the right place. Okay, that was selection sort. We're also going to look at insertion sort today, so let's look at that as well. Okay, this is insertion sort running. Where's the ripple effect come from? Who could remind us how insertion sort works? Yeah.
You start with an empty list, and then you insert items into their proper relative position.
Okay. So let me make the size smaller here. We'll do 8. And I'll just step through it. So what it does is it doesn't worry about the first element. It starts with the second element. So what it does is it moves from left to right. It takes the next element it encounters, and then it tries to put it in its proper position in the sorted array that appears on the left side. So initially, this subarray is sorted as best you can with one element. The rest is unsorted. So what it'll do is it'll compare this guy and that guy, and it will see that this guy is smaller than that one and it belongs before it, and so it'll swap them. So now the first two elements are sorted, and these are the unsorted ones. So we do it again. We're going to compare this one and this one, and it sees that it's smaller, so it moves it below it, and then it compares it to that one, and it's bigger, so it sticks with that. So essentially, the way to think about it, let me step through it one more time. It's going to, every time it finds an element, it tries to push it as far down into this sorted list as it can to its proper location. So let me make it big. You can really see it in action. I'll have to turn the speed up, though. Okay, so the left half is always sorted, not perfect, it's sorted as well as it can be. The right is unordered, and then each successive number is sort of pushed down to its proper location. You're seeing the flickering is the thing being pushed down to its proper position. So that's insertion sort. Any questions I could answer about them before we look at analysis? This is a Java application that's sitting in the schedule if you want to play with it yourself. All right, back to this. Here's selection sort. Now, suppose we're interested in predicting how long selection sort will take to run on an array of length n. One way we could do it is by counting all the operations. We could laboriously count the operations. And I've broken them all down here. Int I equals 0 is one thing. There's a place where we do j is less than data.length and so on. And we can start counting. So how many times will that int I equals 0 be executed?
Once.
Once. No matter how long the array is, that's only done once. How many times will we do I is less than data.length? Yeah, we do it n plus 1 times, it turns out. It succeeds n times, and then the n plus 1 times it fails. So we could keep doing this. I plus plus is done only n times. That int smallest equals I is done n times. That one is done n times. This one's a little bit harder. This j is less than data.length. Okay? It just depends on, it varies as the algorithm runs. During one of the passes, it's only done once. Another pass, it's done twice. Another pass, it's done 3 times. Another pass, it's done n times. Okay? it's sort of turned around. The first pass there'll be n comparisons done. The second pass there'll be n minus 1 and so on. J++ is done that many times, that comparison, and the swap is done once for each number. So we could do that count. It's kind of laborious. We could do it. What will we do next if we're trying to predict the running time of this algorithm?
Look at the longest one.
I said look at the longest one, but what if I want to get a number out? What would you do next? Yeah.
Yes, look at the one that has the largest multiple of n.
Yeah, you're trying to pull a big O analysis out of this, I think. But what I'm going to suggest that you do is, well, let me do this first. What I'm going to do is basically add all those things together to get the timing. But before we do that, we need to simplify those summations. So here's a good handy thing to know. The sum of the first k integers is k times k plus 1 over 2. Okay? Just commit that to memory. So if that's the sum of the first k integers, the sum of the first n integers is n times n plus 1 over 2. What about the sum of the first n minus 1 integers? It's always the last one in the series times the one after it divided by 2. So this would be n minus 1 times n over 2. What about this one? How could we compute that sum right there? The trick in doing these summations of integers, these come up a lot when you're analyzing algorithms, is to rewrite it into a form like that we know how to solve. So how could you turn this into something more familiar? Yeah, factor out the 2, and then you get that times 2. So it's n times n plus 1. What about this one here? How can we simplify that to something we recognize?
Multiply by 2 and add 1?
Let's see what I did. Yeah, so I added 1 to each term. So I made that 2, I made that 4, I made that 6, and so on. So I added 1 to each of the terms. And then I subtracted off the n to get rid of those extra things. We know what that sum is, though. That's just n times n plus 1. So we get that. N squared minus n. N squared minus n. Well, I guess that's just n squared, isn't it? Okay. So we could take this table and simplify it by summing all those series that we have. Then we could say, okay, let's assume the first operation we looked at takes a seconds, and the next one takes b seconds, and c seconds, and d seconds. We could then come up with that as our timing. We could, collect terms like that, and then we could, we could say, okay, that's a constant, this is a constant, and so on, and we come up with something like that. So then, if we wanted to make some exact predictions, how could we predict running time then from that formula?
What's the dominant factor to that?
Well, if I wanted to say that if you give me an array of 1,000 elements, it'll take this many milliseconds.
Just plug in 1,000 for n.
Well, plug in 1,000 for n, but what are C1, C2, and C3? How do we determine those?
Experimentation.
Yeah. We'd have to go experiment and determine how long does it take to assign a number to an element. How long does it take to do a less than comparison? If we could determine all those constants, A through J, then we know C1, C2, and C3, and then we could start making predictions about running time. But that seems awfully complicated. No one wants to do that. But all we care about is doubling behavior. All I care about anyway. And so if you're trying to determine the doubling behavior for a program, then low order terms don't matter. Turns out that if you're looking at doubling behavior, n squared plus n versus n squared, in the long run, the n is negligible. It doesn't contribute to the, they double at the same rate in the limit. And so what I've done here is I just start dividing. What I have over here is f of 2n, and here's f of n, and I do some algebra, which I won't dwell on. And I end up with 4 divided by 1 plus something, and then 2c2 divided by something, and so on. But what's true about all these things that are in red as n gets large? Yeah, no, these things in red go to 0 as n goes to infinity, right? Because they all have n's in the denominator and constants in the numerator. So this just justifies that the lower order terms don't matter for large n. The ratio is going to be 4. So that's good. The running time grows as c1 times n squared. That's simpler than the thing we had before. Okay? Leading constants don't matter either. If we just care about doubling behavior, the c1 gets divided out when we do a ratio. So we don't need to do any timing to predict doubling behavior. We just need to figure out the high order term. The leading constant doesn't matter. The low order terms don't matter. And that's where big O notation comes in. So like I said, when we say that a function is O of n squared, we're saying that, this is sort of informal now, we're saying that its higher order term is no bigger than an n squared term. And it means that in the limit, f of 2n is no more than 4 times f of n. So these are various ways of thinking about it. But just keep in mind, it's an upper bound on the rate of growth. Think of it as an upper bound on the high order term. An upper bound on the doubling behavior. All sort of equivalent ways of thinking about big O. Upper bound on all those things. Now, did you see omega in 2420?
I think so.
Not sure. Okay? Omega gives just as a lower bound. It's a flip side of big O. If we say that f of n is omega of n squared, we are giving a lower bound on everything. A lower bound on the higher order term. A lower bound on the doubling behavior. A lower bound on the rate of growth. Okay? So big O, and if f is O of g, then g is omega of f. Then there's theta. Theta gives you simultaneously an upper and lower bound. So when you say something is theta of n squared, that's a much stronger statement. It is saying the higher order term is n squared. The doubling behavior, it will double. I mean, it will quadruple, let's say. It won't be less or more. It will be quadrupling if it's n squared. It gives you both an upper and a lower bound. So if you can prove that something is O of n squared and also show that it's omega of n squared, then you know that it is theta of n squared. So we always prefer theta bounds to big O or big omega bounds, simply because it gives both simultaneously. It's a more succinct way of saying the same thing. All right, and here's a full table. So let's start with big O, which is the second row up here. If I say f of n is big O of gn, then I'm saying that the asymptotic rate of growth of fn is less than or equal to that of gn. And it's opposite for omega. For theta, you know both. But then we've got these other ones, which you probably haven't seen, little o and little omega. And if O, theta, and omega are like less than or equal to, and greater than or equal to when you talk about rates of growth, big O is like less than, and little omega is greater than. So would it be true to say that selection sort is O of n squared? Yeah. Would it be true to say that it's little o of n squared? Is the rate of growth, well, let's put it this way, is the high order term of selection sort's running time less than n squared? No. So you could say it's little o of n cubed. So little o is characterizes what it means to be a higher order term. The n cubed is a higher order term than n squared. And so n squared is little o of n cubed. And little omega is the opposite, a lower bound. Yeah?
Does big O always have to be least upper bound? Or
No.
can it be any upper bound?
Big O can be any upper bound. So is it true to say that selection sort is big O of n to the 100th? Yes. It's an upper bound. Now, people don't usually do that. People try to make big O as tight as possible. Is it true to say that selection sort is omega of n squared? Yeah. Selection sort always takes to n squared. It doesn't matter. It's insensitive to the running time is insensitive to whether the array is sorted or not, or how it's ordered. So the best way to describe selection sort is to say its running time is theta of n squared. It's both big O and big omega of n squared. So it's theta of n squared. Now we won't do much with little o and little omega. We'll do a little bit with little o. These three in the middle we'll do a lot more with. So just remember upper bound, lower bound for big O and big omega, and then both for theta. So here's some examples. 3n squared plus 5n plus 3. That is O of n cubed, right? N cubed is an upper bound on that. Really, all you have to look at is the higher order term, n squared. N squared is less than n cubed. It's less than n squared log n. It's less than n squared. I should say less than or equal to all of these. Less than or equal to n squared. The rate of growth is the same. Is bounded. It's wrong to say it's O of n log n, for example, because n log n grows more slowly than n squared. So I won't belabor the point, but it's something good to look over to make sure that you understand the differences between these notations. I'm trying to remember where I'm headed here. Oops. Shoot. For some reason it's not letting me back up on the slide, so I've got to go back to the beginning. All right, let me explain a few things. Last thing we'll have time to talk about. You're used to using big O notation, or more generally, all these 5 asymptotic complexity notations to put bounds on specific algorithms, like selection sort or insertion sort. It's also commonly used to put bounds on problems. So you might hear someone say sorting is omega of n. Okay? The sorting problem is omega of n. What that means is the worst case of every sorting algorithm is omega of n, which is to say, in the worst case, every sorting algorithm takes at least linear time. Okay? Is that true? Yeah?
Yeah, because you have to at least check that it's sorted. That requires checking every single element.
Right. Any algorithm would at least have to check to see if it's sorted. It's got to at least look at every element. And that takes linear time. So what this is saying that is no one can ever invent a sorting algorithm that's faster than omega of n. There's going to be some case of it that takes at least linear time. So this is saying something about all algorithms that have been discovered or are yet to be discovered. Okay, here's another one. Comparison-based sorting is omega of n log n. That's something that we'll prove later this semester. That's not as intuitive as the first one. But it turns out that if you're sorting only by doing comparisons, your worst case is at least n log n. And my final point, when you put a big O bound on a sorting problem, like comparison-based sorting is O of n log n, that means something different than the lower bound. The lower bound is putting a lower, if you put a lower bound on a problem, you're putting a lower bound on all algorithms. When you put an upper bound on a problem, like you're saying comparison-based sorting is O of n log n, what you're saying is there is an n log n algorithm for comparison-based sorting. Okay? You're saying that it can be solved that fast. Yeah?
But it's the high usual goals, right? Like it doesn't go
It's what?
It doesn't. This means it does go faster than O of n log n. Is that the last one?
Well, that's still an upper bound.
Yeah, so
I could say comparison-based sorting is O of n cubed. That's just saying that it is possible to sort that fast. In fact, it's possible to sort fast. All right, we'll continue with this next time.